All right, we're going to look at optimization. That's a process of trying to find the maximum or minimum of something. So some of the things we're going to be looking for, find the formulas related to the problem. There's going to be some substitution that comes in here when we combine these ones. And then we know to optimize something. If you want to try to find the maximum or minimum or something, find the derivative, set it equal to 0, and that will give you your minimum or maximum. As we've seen previous to this, derivatives are going to have a max or min, where that derivative is 0, where any point maximum minimum is going to have a horizontal tangent line, which has a derivative of 0. Let's look at an example. Farmer has 2,400 feet of fencing, wants to fence off a rectangular field that borders a river. He needs no fence along the river. What are the dimensions that give the largest area? So we're maximizing on this one. We want the largest area. One thing you can do here, especially a problem like this, maybe draw out a little picture to just kind of help you think about this. So if we got this river here, farmer's building a fence to enclose a rectangle field. Probably doesn't need fence along the river because cattle or whatever is not going to escape through the river. What now are we trying to do here? Well, let's try to figure out what we know and what we have to show here. What do we know in this problem? We know an amount of fencing. Well, fencing's kind of trying to, like, it's talking about the distance around here, or that's the perimeter. So what's the perimeter of our fencing? We're going to need some variables. That's up to you what you want to use, X and Y, or a lot of times people on this one like to use like length and width, whatever you want to use. If we're talking about perimeter, that's the distance around. So we know these opposite sides are equal, and that perimeter is going to come out to be the length plus 2 of those W's. And we know the amount of fencing, so let's put that in. 2,400 equals this. So that's what we know. What are we trying to show? So to go to the question, what are the dimensions of the field that has the largest area? We're trying to maximize area here of this fence. So the area enclosed of a rectangle is just length times width. Now, we know we're going to have to take the derivative of that to maximize it. With 2 variables, that's going to be a little bit hard. We want to, if we can, get down to 1 variable. So we're going to come back to what we know over here. Try to solve that for one of the 2 variables. Pick the easiest one if there is one. Here, L is going to be our easiest one. So what we're going to do, let's minus 2W from both sides and get this, see what L is equal to here. So it's going to be 2,400 minus 2W. Now what we're going to do is take that result here and plug it in for our L over here. So now our area equation becomes 2,400 minus 2W times W. We could find the derivative at this point. It's going to be easier though if we do a little simplifying. Let's distribute that 1W on the outside. Now let's go to our derivative. Okay, to maximize something, find the derivative, which here would be 2,400 minus 4W, and then set it equal to 0. That's where you're going to get your maximum or minimum. So if we set this equal to 0 and solve now, we got 4W being equal to 2,400, and it looks like our width then that's going to maximize is going to be 600 feet. Because that's the dimensions talked about in the problem. It does want the dimensions, meaning it wants us to find that other one too. If it wanted you to find the maximum area, well then find both and then plug back in and find the maximum area. So here, let's find that length. Here's the easiest spot to do that. Our length is going to be 2,400 minus 2 times the width of 600, which will end up being 1,200 feet. So now we got the dimensions of both. We've answered the question. One thing they may also ask, other than like maybe finding the total area or the largest area on this one, might be in the AP test, they might say show that this is in fact a maximum. Either use first or second derivative test to show that. I'll use the first derivative or second derivative test to do that. Here's our first derivative. Let's find the second derivative. So second derivative here would equal, that's a constant, so that's 0. Derivative that's going to be -4. That derivative, doesn't matter what the width is going to be less than 0. Remember from our work with second derivatives, if you have a second derivative less than 0, it's concave down. So if it's concave down, the point here is going to be a maximum. So this shows that we did in fact find a maximum, or the largest area. Let's have you try one. We're going to read through it. It says a manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with max volume? So again, we're trying to find a maximum. Just so we're all using the same thing here, it says it has a square base. So let's call each of these the same thing. Let's go X. And then let's call this height, which could be something different, Y, just so we're working with the same variables. So read through it, see if you can find out what you know and what you have to show here. Try it out, and then after you're done pausing the video, unpause it and check and see how you did. Okay, let's see. What we know here is there's a surface area of 108. So what's our surface area equation for this one? They'd expect that you could come up with this surface area on your own. Note that it is an open box, so we don't need to count the top. So the bottom would be x times x, or x squared for the area. The sides, like one of these sides here, is x times y, and all 4 of them are going to be the same. So there's 4 areas of x times y. And then we know that the surface area ends up being 108. So let's set that equal to 108. What do we have to show on this one? Max volume. So what's the volume equation? Again, they'd expect that you could do this. It's just length times width times height. So x times y, or that'd be the same as x squared y. Okay, now you gotta get this down to one variable. So let's look over here. Which one's easier to solve for? Definitely y in this one. So minus the x squared over there. And then let's divide here by 4x to get y alone. So we got to divide the other side also by 4x. Now we're going to take this result and plug it in for our y over here. And hopefully you did the same. Next step now, we want to do some simplifying. One thing you could do, there's an x here and x here, so we can cancel one of those x's out. And then we're going to need to distribute the remaining x here. So now our volume equation becomes 108x minus x cubed. So got that 4 on bottom. We could do quotient rule. I think it'd probably be easiest if you just made both of these over 4 and then tried to simplify it. So think of it as 2 fractions, both over 4 with that common denominator. 4 goes into 108, I believe. Yeah, so if you divide that, you're going to get 27x. And on the other one, again, you could do quotient rule, but this one's easier if you think of this as 1/4 x cubed for finding the derivative. So now we've simplified that. Let's find out what that derivative is. Derivative would be just 27 there. On the other one, it'd be minus 3/4 x squared. Now set it equal to 0 and solve. I'm going to times by 4 first. So if we times that by 4, you got 3x squared being equal to 108. And then let's divide that by 3. And we got x squared being equal to 36. And so if you take the square root on this one, remember it's plus or minus here, square root of 36, which would be positive or negative 6. So which one's the answer? Well, if we're talking physical box here, we know it's got to be the positive answer, but negative 6 could also be a possible answer. When doing this one, again, you could check You could check with second derivative just to make sure that we're doing the right one with the maximum here. If you plugged in, or let's find the second derivative. So I'm looking here at the first derivative, second derivative, derivative 27, 0. Derivative of the other one's going to be negative 6/4 x. So if we find second derivative at positive 6 here, that's going to give us negative 36/4, which is less than 0. Remember, if we get one like that, that's going to be concave down, which is going to produce a maximum. That's the one we want to use. If you would plug in the other one, you get the opposite result, that at negative 6, this is going to equal positive 36/4, which is greater than 0. That's going to be a minimum. And so we do want to use positive 6 here. Now just make sure you answer the questions. It says again, what dimensions? So we know that our x value here is going to be 6 inches, I believe. Yep, square inches, so 6 inches. What's our y? Best place to find it would be right here. So now just plug in 6 here for our x's and solve it out and see what you get. So that could be like a calculator thing right there you could do. And if you plug that in, looks like the y value comes out to be 3 inches. So that would be the dimensions of the box that give the maximum volume.